Well, thank you for coming. Let's begin with string theory, which is supposed to be the main subject of my conversation. Where does string theory come, and why it's so interesting, and why successful? It depends on whether it fits measurements and experiments. Also, not entirely on sort of aesthetical beauty of the theory. But anyway, it's going back somewhat to the concept of elementary particles. In the old times, let's say at the end of the 19th century, people are beginning to talk about atoms. They didn't quite see them. They didn't have the technology. But there was an atomic theory. I think it gets back even to the Greeks also. And people imagined the atoms as the elementary particles, as atom means indivisible, essentially. And elementary particles, and imagined them as very small spheres, just perfectly round, and some sphere, there were some spheres and spheres. Atoms of oxygen were different from, it wasn't clear how they were. It turns out that truly there are atoms, and they are interesting objects, but they are not spherical. They may have, even the shape of an atom is not, in modern terminology, is not well defined, because atoms are composed elements, and they are made out of a nucleus, and then electrons which fly around according to rules which are rather complicated and dictated by quantum mechanics. And so it was discovered atoms not only are not indivisible, but they are, let's say if you take iron, it's composed of a nucleus, which itself is not a simple object, it's composed of something else, but also of 50 odd electrons flying around. And therefore they are very complex objects. But in any case, each one of these objects was thought to be a kind of sphere, maybe elongated, rotating in some way, but still some small object which was almost round or derived from the sphere by some stretching or squeezing. String theory is departed away from this point of view. Let me go back a little bit. There is also relativity, special relativity, which came into existence when was now it's 50 years ago exactly, with the annus mirabilis, essentially, of Einstein. Not 50, 100 years ago. Sorry, 50 years ago is another thing. Anyway, general relativity has unified space and time. And what we call a particle, it's essentially a very small object lying in our space. But there is another dimension, there's a fourth dimension, which is time. And since this particle exists in all this time, because you can see it through the time moving around, by existing now and from let's say a few seconds and so on. If you think about it, it's a line in the space-time. You add one dimension to space, but you also add one dimension to the particle. Therefore, it looks like a line which is curving because the particle is moving around. And it's like having really a string, but hanging in four-dimensional space. And that was the general idea about an elementary particle. Let me again remind you that elementary has changed meaning throughout history of physics. Things which were thought to be elementary turned out not to be elementary, to be composed of something else. But as we moved out working at higher and higher energy with better equipment. It turns out that what we thought, everything repeated endlessly. What we think it is elementary, in fact, it's not elementary at all. It has always a structure. The other point is that particles tend to be falling in groups of or sets rather than groups of elementary particles which have properties which move from one to the other. You make a jump going from one to the next one, but looking at all them together, then it seems to be some sort of regularity. They form a family of particles having common properties. All this has driven the fantasy of mathematicians and physicists in a manner which I'll try, I hope, to explain, but I'm not that optimistic because it tends to be very abstract, the theory of strings. At any rate, I just told you that in space-time, a particle is not a point, but it's a line which contains all the positions throughout times of all the particle itself. And somewhat, the idea, there has to be a higher principle. It tells you how the particle moves. And the way the particle moves is like I would take this is a string of some sort. Imagine it's the trajectory of the particle. It should be the trajectory of particle, but it's curving, it's wiggling, it doesn't look good. Physicists think that you should pull it. And that gives you the true physical theory of a particle. There has to be some principle, because the principle of action, in fact, it goes back to Lagrange, who was a fellow from Torino, and the theory of action, and the straight thing, the one which is pulled, obtained by pulling, is the trajectory throughout space-time of the particle. Notice that so space falls only in this way, time runs along the string. That is cutting here, cutting here, cutting there, gives you successive positions of the particles. Now, this gave some idea. People said, why should we consider a particle which is just made out of something which is a point, or a point with around a little bit matter, but still very small, small object? We cannot think about an extended object, still rather small, but which has much more, much lively, much more complicated, much more structure inside. It is hard to describe the beauty of a mathematical equation. It has to be in and be explained why sometimes you write it in some way and some genial fellow comes about and tells you, oh no, you can write it much better, this is much beautiful, this is much more compact and explains many more things. So there is a beauty which is hidden. You have to be inside. It's like understanding, I don't know, modern music. Not everybody can do that. And therefore, you have to be in the story to be able to appreciate the beauty of a mathematical theory. Anyway, the interesting thing is that people thought about some object which, instead of being just a line, moving a little bit thick but not much, going through space like that, it's a surface. It's like being the wall of a pipe. Or you cut it and you get a ring, something circular with closing itself. If you move it around, you get a pipe. Or it could be just a segment which is open like a stick, and you move it around and you get a strip, which keeps on curving according to the dynamics of the problem. And people have been devising, again, beautiful ways of telling how a string should move through space-time. And if you do that, that you get string theory. It has some analogy. In fact, there is some deep analogy between this type of mathematics and it sounds strange, the one soap films are made of. If you dissolve soap into water, and you take some, again, a ring of metal, you put into the water, pull it out, and you see there's a film forming with the boundary on the ring. You can do that. If the ring is wiggly, is being bent, although the surface inside bends. But it has one property which is interesting, is the surface, is the film hanging of minimal surface. As the one tends to get tighter and tighter, and it pulls, and it gets a minimal surface. Something similar happens in an elementary particle described by string theory. It forms a surface in four-dimensional space, and it's like a soap film. That is, even that surface tends to be smooth and pulls into itself, and then that determines the trajectory of the string. Now, the ways a small particle may vibrate and the ways a string may vibrate are completely different. The string can sort of twist around much more easily, and therefore all the modes of vibration of a string are like the notes, the sounds emitted by the chord of a musical instrument. It plays, and it gives you definite frequencies which correspond to different particles, essentially. So looking at the particles like listening to a piano, where you get somebody playing the piano. And so if you study hard enough, you go in and look at the table of particles, and you like hearing music. I'm exaggerating a little bit, but you have to be inside the whole thing. So this thing vibrates. It can describe families of particles, which are related one to the other. It's not complete the job. We still have to go a lot to do a lot of work and to go ahead and to do more measurement and to discover more particles. The more we see them and we align themselves and get into a family, the more you know about the family. And that's more or less what string theory is about. I warn you, it's mathematically, it's unbelievably complex. And because string theory, as they do now, I was being optimistic. They live not only in three-dimensional space and one of time, but some of them reach 1,000 dimensions, and 12 in a space which has 11 dimensions and one time, and they move in a complex way. You see only 3 of the dimensions which we are used. The other ones are hidden in the microcosmos, and it's immensely complicated. And my suggestion is that if you are not don't have much mathematical knowledge, keep off from it, because it will just discourage you, and it's not exactly what we like to do. I would like to add, after this sort of entrance into string theory, I would like to sort of move a little bit away and talk about art and science in more general terms. When I was a kid going through high school, it was elementary school I did during fascism, just before the war, and the high school essentially right after the war. But the prevalent ideology at that time, cultural ideology, was the one of neo-idealism. And for some reason, which I never understood, Italian philosophers, Benedetto Croce was one of them, actually the most prominent one, didn't like science. And therefore, there was a heavy emphasis on art, especially on Italian literature, and also on philosophy. But science was kept on the side. And this produced a negative attitude, cultural attitude towards science, which is still present now, although not in a disastrous way as it was at that time. But my personal experience in going through that, I loved science already. I was very interested in math and in physics, although in manner which now would be very primitive. And I acquired an instinctive distaste for some forms of art. Second-rate Italian literature I don't like. I like music because they sent me to learn the piano. I am a horrendous pianist. Now I cannot even claim I play it because I'm out of commission. But I always loved music. And I also like sort of paintings and visual art, etc., etc. Why not? And I can, let's say, this taste which Italian philosophy I had for science, I didn't pay it back. That is, I'm still interested in things outside of science. And so are many colleagues of mine. I remember that in some spectacular way, I went to some scientific meeting in Vienna. And the meeting was, took place in the Kaiserhof, I think the imperial residence, what was the imperial residence. And then one day I was a little tired of seeing slides and one thing or the other, and I went out. And as I was moving out, there was, toward the exit, there was a young girl with a small table and some pieces of papers on the table. I asked her, "What are you doing here?" She said, "I'm going away, free ticket for the opera." And for whom? For the physicist. "You want one?" "Yes," I said. "You also want for your wife?" "Yes," I said. And then I took the ticket, and they were for the Don Giovanni, with the best performance of that time, Cesare Siepi, Gundula Janovic, a director was Carl Böhm, and it was top. And so I went to listen. I never listened and heard Don Giovanni directly before, so we went there, and the first 5 rows of the theater were filled with physicists, solid. They all took the ticket. Nobody refused it. And they all enjoyed the opera, me too. I fell into kind of a trance. It was a splendid performance, which I'll never forget. Then in front of the palace also there was a museum, and I went there and they had 13 Bruegels, the best one in the world, and it was really worth doing it. And I didn't feel at all that I had to remain in a world without art. It's one of the ways human beings express themselves, and I welcome it. I may quote, changing a little bit subject, another historical point of contact between art and science. Few people realize that the important role of great artists in the Italian Renaissance, Leon Battista Alberti and Piero della Francesca, for example. There is a famous painting of Piero della Francesca. He was born in 1415. I think he died at the time of Columbus, exactly 1492, if I recall. And in Urbino, there is a small painting which still now historians of art don't decode easily. They call the Flagellazione del Cristo, whipping of the Christ. And what is interesting, there are 3 guys talking, nobody knows who are they. Anyway, that doesn't so much matter, but there is a Christ sitting in some kind of a corridor, and the important fact that the perspective of that thing is perfect. If you look at paintings before, done a century before, there is laws of perspective in Giotto are not that well respected. Therefore, and also the same Piero della Francesca wrote a manual, Ars Pingendi, in which he explains these laws. And a lot of people tell me that he was also a great mathematician, not only a great artist, because discovering the laws of perspective open up the way to projective geometry, which is an important step in modern mathematics, and which is extremely important in many ways, and open up to group theory a lot of development around. But the origin of this geometry comes from, and the trust comes from developing laws of perspective. And therefore he was also, of course relative to his own time, it's half millennium ago, he was a great mathematician, a man who also explained clearly put forward a number of very interesting points. Therefore, it would be unwise and unfair to divide sort of scientific culture and sort of art and other type of culture. The point is that we have to find points of contact where information can flow up and down, so to speak, and bring some interesting results. Let me say, I have to. The image here disappeared, and I don't know how to call it. Borzani is around. Oh. That's Salvatore Dali. It's a well-known painting, and however, I wonder if look at the cross, which is the interesting part. It's not an ordinary one, in the sense it's made out of cubes glued together. And if you count them, there are 8 cubes altogether. There are 4 lateral ones and 4 on the vertical. There are 4 of them. Therefore, it looks like a cross, but instead of having just 2 arms, it has 4 arms. It has east-west, but also north-south, a block. And why that is interesting to mathematicians? Because that's, let me make some analogy. You have a box made out of cardboard. Like you go buy anything, it's always in some sort of cardboard box. Let's suppose it's cubic. And if you open it, it will open up, and you can flatten it and put it on a table, and you'll get the 6 squares of the cube. It lost 1 dimension, but you get something flat, but you get the 6 squares, which is a cross, essentially. Well, what Dali discovered, he knew, I don't know exactly how he got at that point, and that this is the same procedure, but done in 1 dimension more. You start with a hypercube in 4 dimensions, which has 4 dimensions, has walls with 1 dimension less, which are 8 cubes. If you unfold it in 3 dimensions, like the analog of flattening it in 2, then you get this cross of Dali, made out of 8 cubes, all glued together. Therefore, Dali knew something about the 4th dimension. I met Dali once. I didn't talk to him, but I was close by. I mean, succeeded in having a picture taken of myself. He was presenting the Bible according to Dali. And to Dali. And of course, I was a young fellow. I went back of Dali when they were taking pictures of him, and then I have a picture of myself with Dali. And that's, for me, it's a great memento. I have hanging on the wall of my home. And even at that time, I had mustache in Dali style, and that was fine with me. And we take the piece. Dali spoke muttered. It was not really speaking. It was emitting sound. And sometimes I recognized some English words, Spanish one, French, and I think Catalan too. I was talking like that, and we couldn't make any head or taste of what he was talking about. But anyway, he was interesting. But didn't produce any 4-dimensional object when he was there. I haven't seen the Bible according to Dali. However, later on, speaking to an American mathematician, I think he was from, I forgot exactly where he came from. And he told him he was working on some field which would interest aesthetics or mathematics or something. I'm sorry about not being in details, but it's something of 30 years ago, roughly speaking, so I cannot quite remember all the details. He told me that one day Dali phoned him. and said he wanted to talk to him about something about mathematics. And he said yes. He came down and had a long conversation with Dali, asked questions. And he told me Dali had an uncommon mathematical culture, was asking pointed questions, sometimes also very technical thing in details. It didn't look at all the crazy fellow which he showed up to be in public. When he was there, he went to business. And he asked really pointed questions and showed that he was he knew mathematics, more than the man on the street. And therefore, this is an interesting point of contact. And I had this painting is the proof that he knew what a tesseract was. I mean, the hypercube, an idea of what the fourth dimension was and in what sense it can be done. I can spend a couple of minutes to help you imagine the fourth dimension. If you take a square, and then you shrink it a little bit and you get a smaller square inside. Then you join every vertex of the inside square with the vertex outside, and you get big square, the one inside, and 4 lines joining the two. That looks like the perspective of a cube seen from the side. Or it's like this room. You can see a rectangle which is the end of the room, and there is another one on the back, and the lines which are joining it. And therefore, that is that. So you miss. You can see the 6 faces of the cube because there's the big one front, which covers all the other one, and then there are lateral one and the one at the end. You can do the same thing with a cube. Starting from a cube, you shrink it and you put another smaller cube inside, and you join things. And then it becomes a perspective of the hypercube in 4 dimensions. The trouble is that the human mind is not made to extrapolate to 4 dimensions. Anytime you try to go into 4 dimensions, it drives you crazy because you cannot imagine. We don't have the neurons adapted to register 4-dimensional images, and we do not have. However, this painting for me, the first thing that came to my mind when I was supposed to speak about art and science. How long have I been speaking? About half an hour. I may stop here. If you have any questions, maybe it will induce me to give some answers, and maybe I can talk for the remaining 15 minutes. I'm told to speak 45 minutes, if you agree to that. Anybody? In appreciation of art, beauty, you do. There's no a priori rule for painting or doing music. It just has to be beautiful. The problem is that you need to have, for music, to have ears. We can listen to music, or if you visual art, you have to see the painting, or somebody explaining it to you, or get some way somehow into the problem. Relativity is the somewhat epitome of something which is not understandable. Very hard to understand, and however, when he began studying relativity, they published a booklet by Einstein himself, The Meaning of Relativity, was also translated into Italian. I learned relativity into that. And I read it with great enthusiasm. For me, it was absolutely beautiful. And the same I had when I read the book of Dirac on quantum mechanics, which was a milestone in quantum mechanics. Why it was beautiful, I don't know how to explain. It showed me connections between objects I knew, but which I did not suspect there was a connection one with the other. And they came from unexpected directions. And it made my vision of physics and of the world microcosmos much more interesting. It suggested ideas or asking questions of one sort and the other. Therefore, there's a form of appreciation which unfortunately is not accessible to the layman. You need to know some technicalities. Therefore that makes life harder. But for me, it was a form of art anyway, because it was beautiful. And what else can you ask? Relativity. Relativity, the interesting special relativity. General relativity is very beautiful. It's absolutely splendid theory. But it was so kind of the hardest theory ever put around to explain, because you need to go into so much technicality that you cannot do it. Special relativity might be, I can give you some small taste of special relativity, which is considered as explaining art, if you like, and is the following, that as I speak to you, sound is coming out of my mouth and moves throughout the air of the room at about 300 meters per second in all directions. However, if wind is blowing, I would be in open field and wind is blowing and it has a certain speed, I had to add the speed of compose, as they say, it is the speed of the sound with the speed of the wind. And the sound would move faster downwind and slower in the other direction. And therefore, it would not be the same, it would not propagate sound with the same speed in all directions. It changes. Now, at the end of the 19th century, people thought that light was similar to sound. It was a wave which would propagate into something which took the place of air. They called it ether. And just like air had wind, ether had to have wind. And they sat down to spend some money, to do some experiment, famous Morley experiment, in which they wanted to measure the speed of ether wind. And maybe they measured today there was no wind, but as the Earth was going around the sun, it would change continuously speed, and therefore, at the opposite point of the orbit, it would show some wind, because we were moving exactly in the opposite direction. It would change the direction, the speed of the wind by up to 80 kilometers per second. So that would be perfectly measurable. And they did the experiment and saw no wind. And that put them in a great embarrassment. They didn't understand what was going on. And they made several hypotheses. Still, Einstein came about, and I make a short story of what this actually lasted 20 years. But with the Annus Mirabilis, the one we are celebrating now, he said there's no ether, or at least the role of ether is taken by space-time. Space itself is the one which, so to speak, vibrates and transmits light, regulated by the so-called Maxwell equations. And a crucial role is played by the speed of light. Physical phenomena change completely if you try to move, if you take phenomena in which there are particles of things moving at the speed of light. And therefore, it happens that light is a kind of a sound, moves through ether, but if you add to the speed of light anything, you get back the same result as before. It doesn't change. You get intermediate results, if something moving half the speed of light, and you add something which is a wind, which is 1/3 and then instead of adding the two, you have always to correct and subtract something. The formulas are more complicated. Therefore, this showed that you start from a simple hypothesis and test out that you get to some other world, which was a space-time of Minkowski, in which, so to speak, space and time are unified, 4 dimensions, one inside the other. Unification on the equation looks very beautiful. Once you've seen it, you don't forget it. Imagining it, it's harder. because the effect on human life, if we could move to the end of this room, moving at a fraction of the speed of light, like half speed of light, a lot of incredible phenomena would immediately be visible, which are not visible at this moment because they are, we would take very precise measurements to put them into evidence. But so to speak, if I would move toward the end of the room down there, all persons in chairs and everything inside the room, to me, it would look like they squeezed in the direction of my motion. Events which are simultaneous, they would not be simultaneous if I keep on moving. The event toward which I am moving would occur before the one I am leaving. And therefore, there are all sorts of relativistic effects which are totally, I say, coherent one to the other. You cannot have one without having the other, as you get into contradiction. But with human being are totally not human. You have to see them written in formula, which are very beautiful. If you look at them, you discover these formulas recall you something else, which you have learned somewhere else, and suggest you to do some checks and control. Suggested by now 100 years have gone by. And therefore, that's what physics makes, and for me, very interesting physics, because it keeps on formal analogy to suggest the analogy between phenomena which on surface look completely different. That's beauty. It's a kind of hidden beauty. I don't know whether I cannot ask you to go out and begin to study relativity, but at least what we can do, also for future generations, not to divide art and science. That's an important message. We have to appreciate that we are human beings. We can do better certain things and not others, and vice versa. And I wouldn't just begin saying that all men are brothers, but at least we have to be more comprehensive and understanding and motivation one of the others. And now I am quitting. I'll go home, and I promise you I'm going to listen to some classical music, so that will make me happy.